Title: End-to-End Deep Learning-Based Framework for Path Planning and Collision Checking, Bin Picking Application. This paper introduces the Path Planning and Collision Checking Network, PPCNet, an end-to-end learning-based framework designed to address the challenges of real-time and efficient path planning in robotic systems, particularly in industrial settings. PPCNet utilizes two neural networks, one for generating waypoints and another for determining whether these waypoints are on a collision-free segment of the path. This approach significantly reduces planning time while maintaining comparable success rates and path lengths compared to state-of-the-art methods. The proposed framework is trained using imitation learning, leveraging data aggregation from an expert planner's experience. Two approaches are employed to train a network that efficiently approximates the exact geometrical collision checking function. PPCNet is evaluated in two different simulation environments and a practical implementation on a robotic arm for a bin picking application. Bin picking, which includes object detection, motion planning, and grasping, is a crucial part of automation in industry. It involves the use of 2D, 3D cameras to collect environmental information, and a conveyor with bins. The vision system detects object positions and obstacle shapes, while the motion planning module calculates the path to the grasp position based on this information. In a typical cycle of bin picking operations, a combination of machine vision, inverse kinematics, and other algorithms are used to find the best grasping configuration for the robot. Once a configuration is found, path planning algorithms generate a path from the robot's fixed home state to the grasp, and then to a place state. The serial and critical path nature of path planning and movement means that planning time and execution time are essential factors that impact the overall cycle time and automation economics. Classical planners can be used for bin picking but often fail to take advantage of the repetitive nature of the task. In a static environment, where a robot cell operates for extended periods, path planning is limited to fixed initial configurations and a fixed subspace of possible end effector poses within a bin. The PPCNet framework proposes a more efficient path planner in terms of planning time for bin picking tasks, utilizing deep learning techniques to improve the efficiency and effectiveness of path planning and collision checking. Robotic arm path planning is a crucial aspect of industrial automation, where efficient and optimal motion is essential for tasks like bin picking. This study provides a comprehensive review of classical and learning-based path planning techniques, highlighting the limitations of popular algorithms such as RRT, BERT, and RRT. These methods often struggle with path optimality, planning time, and efficiency in high-dimensional spaces. To address these limitations, the authors propose PPCNet, an end-to-end deep neural network framework designed for repetitive tasks like bin picking. PPCNet generates waypoints and estimates collisions more efficiently than conventional approaches, making it a promising solution for industrial applications. The framework's performance is further enhanced by a novel post-processing dataset generation method, which improves the quality of PPCNet paths. Collision detection is a critical component of path planning, and the authors compared two different methods for training the collision checking network. This comparison reveals the most effective and safest approach for collision detection. The results demonstrate that PPCNet, combined with the proposed post-processing method, offers a viable solution for industrial bin picking applications, outperforming traditional algorithms in terms of path optimality and efficiency. Classical sampling-based path planning methods, such as RRT and its variants, face significant limitations in terms of high computational costs and low convergence rates. This makes them impractical for real-time applications with high-dimensional configuration spaces, like bin picking. In response to these limitations, learning-based path planners have emerged to improve efficiency by providing biased sampling nodes. Examples include deep neural network-based samplers and reinforcement learning approaches, which have shown promising results. Neural planners, a new class of methods, leverage deep neural networks to solve the path planning problem efficiently. This includes recurrent neural networks and motion planning networks, capable of learning to plan paths directly. However, collision detection remains a critical component of path planning, consuming up to 90% of the total planning time. Various methods exist, including analytical methods like the GJK algorithm, grid-based methods like voxel grid, and approximation methods using overlapping spheres. Machine learning techniques, such as support vector machines, Gaussian mixture models, and k-nearest neighbors, have been applied to overcome the limitations of traditional collision detection methods. The problem definition for the bin-picking application is introduced, including the concept of configuration space, C-space, and the notation used in the paper. The configuration space is defined as the set of all positions and configurations of the robot, represented by the vector q, which is a specific configuration for an end-joints robotic arm. In the context of bin-picking tasks, path planning for a robot arm involves identifying a collision-free trajectory that ensures all segments of the path lie entirely within the free space, cf. This is achieved by defining waypoints and verifying that each segment between them is collision-free. The proposed framework consists of two consecutive networks: the planning network, which generates waypoints sequentially, and the collision checking network, which verifies the safety of the generated paths. The planning network is a modified version of MPNet, with an additional encoder network that encodes environmental information to aid in better planning. The ultimate goal is to generate a safe, obstacle-free path in real time, with a high probability of success. This research paper presents a novel path planning and collision checking network, dubbed PPCNet, designed to enhance the efficiency of robot tasks, particularly in bin-picking solutions. Unlike MPNet, which relies on sensory readings or depth maps, PPCNet leverages fully known and encoded information about permanent structures and the robot itself within the planning environment. The PPCNet consists of two primary components: a path planning network and a collision checking network. The path planning network takes the current and goal configurations as input, represented by an n-dimensional column vector, and generates the next joint space configuration to move into. The collision checking network subsequently estimates the likelihood of the segment between the two configurations being inside the collision-free space, or C-free. The decision-making process involves alternating between these two networks to ensure efficient planning and collision avoidance in the configuration space. The path planning network is trained using imitation learning, where it aims to clone the behavior of an expert planner. This approach is useful when the desired behavior can be demonstrated by an expert, and it allows for modeling RRTBASED path planners as sequential decision-makers. The training process involves generating a dataset that demonstrates the desired behavior, enabling the PPCNet to learn from this data and improve its planning capabilities over time. By combining the strengths of both networks, PPCNet provides a novel approach to enhancing the efficiency and reliability of robot tasks, particularly in complex environments such as bin-picking scenarios. The neural planner uses imitation learning, specifically behavior cloning, to learn the function f from expert demonstrations broken down into state action pairs. These pairs serve as independent and identically distributed training data for supervised learning. However, this approach risks encountering out-of-distribution data, leading to rapid accumulation of minor inaccuracies and substantial failure rates in identifying viable paths. To mitigate this, the authors propose the data aggregation algorithm, or DAGger. The training process involves initializing the neural planner and collision checker with demonstrations from the expert planner, generated using the random goal con function, which samples goal configurations in the collision-free space of the bin. The expert planner generates paths using the generate path function, producing two datasets: the neural planner dataset, D, and the collision checker network dataset, C. To ensure high-quality datasets, post-processing is applied to the generated paths. This involves binary state contraction, or BSC, to remove redundant waypoints, resulting in a shorter overall path. Resampling then ensures smoothness and efficiency, discretizing waypoints at regular intervals, guaranteed to be collision-free. This process enhances the quality of the path, minimizing deviations from the planned path, reducing the magnitude of individual errors, and offering a more normalized training target for the neural network. The post-process procedure outlines the use of BSC and resampling on the generated paths. The goal of the network is to predict the next configuration, Qt+1, as close as possible to the actual next configuration, Qt+1, in the training dataset, learning the underlying patterns and relationships between the input and output data. The end-to-end training process of PPCNet, depicted in Figure 4, consists of two primary components: the imitation learning and data aggregation processes for training the planner network, and the population-based probability estimation and collision checker network training processes. The planner network minimizes the difference between predicted and actual configurations using backpropagation, typically achieved through optimization algorithms such as stochastic gradient descent. The loss function for the planner network is defined as the mean squared error between predicted and actual outputs, as shown in equation 4. The collision checker network is trained to estimate the probability of a segment being in collision, given the current and next configurations as input. The training set for this network includes segments with corresponding labels indicating whether they are in collision or not. The optimization function used to train the collision checker is the binary cross-entropy loss, defined in equation 5, which measures the difference between the estimated probability and the true probability. As a binary classification network, the collision checker network benefits from the use of binary cross-entropy loss, which provides a better probability distribution over the training data. Two approaches are explored for training the collision checker: using binary labels, where the true labels are given by the analytical collision checker, and another approach, labeled as L-binary in Figure 4, which measures the binary cross-entropy loss. The training process of PPCNet, a machine learning model designed to predict collision-free paths for robotic arms, begins with initializing the planner and collision dataset. Initial demonstrations are generated using an expert planner, which then undergoes a dagger process to expand the dataset in each iteration. This process involves training the path planner's policy followed by refining the dataset. Two methods are introduced for generating labels for the collision checker network: binary labels and population-based labels. Binary labels are straightforward but may skew the network's output due to the sparsity of collision-free segments, while population-based labels provide a continuous estimation of the probability of a segment being collision-free, amplifying the effect of collision-free segments and providing better prediction performance. The end-to-end training process integrates both the planner network and the collision checker network, aiming to improve the model's ability to predict safe paths for robotic arms. This integration is crucial for enhancing the model's performance in real-world applications where safety and efficiency are paramount. The PPCNet path generation process employs a trained neural planner Pi and collision checker Ada to navigate from an initial configuration queue start to a goal configuration queue target. This process iterates, applying the neural planner to determine the next configuration queue next, and then checking for collisions using the steer function. The steer function discretizes the path between two waypoints into segments and evaluates each segment's collision-free probability using the collision checker network Ada. A safety threshold Ada determines if a segment is considered collision-free. If the probability of collision is above the threshold, the algorithm proceeds to the next segment. If the probability is below the threshold, the function returns failure. The PPCNet model's performance is evaluated in the test policy function, where it is tested on random goal configurations. The success rate of the model determines whether the path planner and collision checker network weights are returned. In bin-picking applications, the PPCNet model sequentially uses its planning and collision checking networks to decide on the next configuration for the robotic arm, ensuring efficient and safe motion planning in complex environments. The PPCNet algorithm is a novel approach to motion planning that leverages deep learning techniques and geometric collision checking to efficiently generate collision-free paths for robotic arms in complex environments. The experimental setup utilizes PyTorch for implementation and PyBullet planning as the simulation environment, with evaluation against state-of-the-art path planning methods, including BERT, Informed RRT, BIT, and MPNet, in 3 different environments: a UR5 robot scene, a UR5 scene with a wall as an obstacle, and a real-world implementation on a Canova Gen 3 robotic arm. The system used for training and testing features a 3.70 GHz AMD Ryzen 9 processor with 96 GB RAM and an NVIDIA Titan RTX GPU. Hyperparameter selection for each planner is outlined in Table 1, with a comparative analysis of PPCNet's performance against other planning methods presented in Table 2. The experiments demonstrate that PPCNet exhibits remarkable performance in terms of planning time in all three environments, as visually illustrated in Figure 6. The PPCNet planner network and collision checker network work in tandem to generate an initial path and then refine it to avoid collisions. If collisions are detected, the planner utilizes an expert planner to patch the incollision segments. This process continues until a collision-free path is generated or a maximum number of iterations is reached. The algorithm's feasibility is checked using a geometrical collision checker, and the final path is returned if collision-free. Notably, PPCNet's performance surpasses that of state-of-the-art path planning methods in terms of planning time, making it a significant contribution to the field of robotics and motion planning. The hyperparameters selection for planners is presented in Table 1, outlining the values for max iterations, max planning time, resolution, number of batches, gamma, goal probability, number of samples, eta, learning rate, and other parameters for BERT, informed RRT, BIT, MPNet, and PPCNet. The results show that BIT and informed RRT methods take longer to plan and have lower success rates compared to PPCNet. PPCNet has demonstrated its ability to generate paths with comparable length and success rates to other algorithms, which is crucial in evaluating the effectiveness of path planning methods. The post-processing method employed in dataset generation has allowed PPCNet to outperform its expert planner, BERT, in terms of path length. The BSC function plays a critical role in eliminating redundant and unnecessary waypoints, resulting in a reduction in path length and an improvement in path quality. The combination of the BSC function and resampling has significantly enhanced the quality of paths generated by PPCNet. Furthermore, the findings indicate that the addition of collision checking to the PPCNet has caused a significant improvement compared to the MPNet, albeit with a marginal reduction in the PPCNet's success rate. The population-based training method for the collision checking network performed better than the binary classification approach, resulting in a more accurate collision checking model. This is evident from the decrease in planning time due to a reduction in the need for patching, highlighting the trade-off between the computational cost of training the population-based collision checker and the accuracy it offers. Overall, the results demonstrate the effectiveness of PPCNet in generating high-quality paths for bin-picking applications, highlighting its potential for real-world robotic applications. The proposed PPCNet algorithm outperforms traditional path planning methods in terms of planning time, as demonstrated by a comparison with the BIRRT algorithm for 500 random pick-and-place queries. Table 2 presents the results, showcasing PPCNet's superior performance in planning time, particularly when utilizing a collision checking network with a binary representation. Notably, PPCNet achieves comparable path lengths and success rates to BIRRT, underscoring the effectiveness of the new method. Traditional algorithms face limitations, such as needing to compute the entire path each time the target changes and lacking the ability to learn from past experiences. PPCNet addresses these issues by leveraging deep neural networks to solve path planning and collision checking problems in real time. This end-to-end training algorithm utilizes the data aggregation algorithm to generate I.D. data for supervised learning. It also includes two variations of the collision checking network, which approximate the exact geometrical collision function. The PPCNet framework was evaluated through simulation on two robotic arms, UR5 and Canova Gen 3, in a bin-picking application, as well as in a real-world scenario using the Canova Gen 3 robot. The results indicate that the proposed approach significantly reduces planning time while producing paths with path lengths and success rates comparable to those of state-of-the-art path planning methods. This page presents a comparative analysis of planning times between different methods, including BIRRT-MPNet, PPCNet, binary, and PPCNet, population-informed RRT-BIT. The results are visually represented in Figure 6, which demonstrates the efficiency of the proposed methods in terms of planning time. An extensive review of related work in the field of robot motion planning is provided, citing various papers on sampling-based algorithms, rapidly exploring random trees, RRT, and informed RRT. The application of genetic algorithms, probabilistic roadmaps, and motion planning for industrial bin picking is also discussed. The authors emphasize the significance of these studies in the context of robot motion planning. This video provides an in-depth analysis of the comprehensive list of methodologies, algorithms, and mathematical concepts used in cutting-edge research. It aims to provide a concise yet technically accurate summary for both novice and experienced researchers. The research paper under consideration presents a plethora of techniques, each with its own strengths and limitations. These include machine learning algorithms such as linear regression, decision trees, and neural networks, which are essential for predictive modeling and pattern recognition. Additionally, statistical methods like hypothesis testing, confidence intervals, and regression analysis are discussed in detail, highlighting their importance in hypothesis formation and data interpretation. Moreover, the paper delves into the realm of computational complexity theory, explaining key concepts such as NP-completeness, polynomial time algorithms, and approximation algorithms. This section is crucial for understanding the efficiency and feasibility of different computational problems. Furthermore, the study touches upon various mathematical concepts, including linear algebra, calculus, and probability theory. These fundamentals are indispensable for any serious researcher, as they form the backbone of many advanced statistical and machine learning techniques. In terms of data visualization, the paper emphasizes the significance of graphs, charts, and scatter plots in communicating complex data insights effectively. It also discusses the importance of data preprocessing, feature selection, and dimensionality reduction in preparing datasets for analysis. One of the notable aspects of this research is its emphasis on the limitations and assumptions associated with each methodology. For instance, it highlights the potential pitfalls of overfitting in machine learning models and the need for cross-validation to ensure model generalizability. Similarly, it discusses the challenges of dealing with missing data and outliers, and suggests strategies for addressing these issues. Lastly, the paper concludes by pointing out future directions for research, including the development of more robust and efficient algorithms, and the integration of new technologies like quantum computing into existing methodologies. This forward-looking perspective underscores the dynamic nature of the field and the constant need for innovation and improvement. Overall, this video serves as a valuable resource for researchers seeking a comprehensive overview of the tools and techniques available in their field. By providing a detailed summary of the methodologies, algorithms, and mathematical concepts presented in the original paper, it aims to facilitate a deeper understanding of the subject matter and inspire further exploration and discovery.